Hey guys, what's up? Welcome to another edition of Some Good Science, coming to you semi-live from my kitchen table. Okay, so this week we're going to talk about Venus and how Venus compares to Earth, kind of review a little bit about astronomy and how Venus's atmosphere is different from Earth's atmosphere and why that is. So just to start this off with, the first page in your slides is a picture of Venus' surface covered. It's covered with clouds, but that is an actual picture of the surface of Venus. But most of the time it looks like this on the right-hand side. And this is some data about Venus, and some of it you actually already know from your reference table, all right? If you want to follow along, some things you're already familiar with. It's obviously closer to the sun than the Earth. Its orbit, its eccentricity, or its shape of its orbit is very circular, very low eccentricity, not oval at all, like Mercury, for example. And its orbital period compared to its rotational period. So again, its day is longer than its year. I was talking with a couple of students yesterday. We were saying how, imagine how long or how many hours or how many days actually a sunrise would be on Venus. Pretty crazy to think about that. And if you were to create a calendar on Venus, what would that look like? One big square, maybe, I don't know. Its tilt, I wanted to point out to you. Its tilt right here. It says it's about 3 degrees tilt. So it's almost, there's hardly any tilt whatsoever. So meaning that it gets pretty much equal amounts of sunlight all year long. Well, anything else I want to point out there? No. Oh, just its mass and its diameter is similar to Earth. So that's why we call Venus our sick and twisted twin sister. You can see that its atmospheric composition is mostly carbon dioxide, okay, 96%. Whereas on our reference table, if you guys remember, this trace amount right here, okay, is 1%, which includes our greenhouse gases like carbon dioxide, methane, water vapor. But you can see it's and only 3% of nitrogen for Venus's atmosphere compared to 78% for the Earth. All right, let's get going. Some questions. You could see Venus. It is a bright morning star or the evening star. It's very, very bright in the sky. Lately, I've seen it. I haven't looked lately, but lately I've seen it in the northeast part of the sky just after sunset. It looks really bright. And the reason why it's bright is because the sun reflects off of all the clouds and makes it look brighter than most stars, most planets. What is strange about the rotation of Venus? We'll talk about that. And in what ways does Venus' atmosphere differ radically from our own? We'll show you some slides. We just touched on that just a moment ago. Why do astronomers suspect there are active volcanoes on Venus? Also think about why is there almost no water on Venus today? And why do astronomers think that there was once water on Venus? And does Venus have the same kind of active surface geology as the Earth? So is it as geologically active as the Earth? I don't want to point that out, but I do want you to see that Earth is in its orbit and Venus, if Venus is closer to Earth in its orbit, it'll appear brighter as an evening or morning star. But when Venus is in its orbit further away from Earth, then it doesn't look as bright. Okay, and the surface of Venus is hidden behind a thick, highly reflective cloud cover. Venus is similar to Earth in its size, mass, average density, and surface gravity, too. It is covered by unbroken, highly reflective clouds that conceal its other features from Earth-based observations. So the first slide you saw was the surface of Venus stripped away from its clouds, but the clouds are so thick, it's hard to see through unless you get some sort of probe going through those clouds. And most of the time, it reflects so much sunlight that it is able to, the clouds are so thick that the sunlight is bouncing and reflecting off of the tops of those clouds, just like here on Earth. But I mean, Venus is just completely blanketed by these thick and toxic clouds. In 1962, the unmanned U.S. spacecraft Mariner 2 made the first close by of Venus. So one of the questions too was, how is Venus's motion different from Earth? Venus rotation is slow, as we talked about, but it also rotates backwards. So this is a picture of well, let's say these are all the other planets in the solar system. And if you're looking down at its northern axis, you could see that the planet rotates in a counterclockwise direction. Again, if you're looking down at the northern part of the axis, the rotational direction is still counterclockwise too. Not rotation. Sorry, it's early. Its direction of revolution, okay, is still counterclockwise. And most planets exhibit this, what we call it a prograde, pro meaning forward rotation. And the direction of the planet's rotation around its axis is the same as the direction of orbital motion. Okay, so counterclockwise for rotation, counterclockwise for orbital direction. Now over here, what's going on with Venus is it has a retrograde rotation. And its direction of its orbit is counterclockwise, like all the other planets in our solar system. However, Venus's rotational spin goes in the opposite direction, still looking down at the northern tilt of the axis. But it is, we call retro meaning backwards. So it goes in a clockwise direction. Its rotation around its axis is in the opposite of the direction of orbital motion. Okay. Venus is slowly in a retrograde direction with a solar day of 117 Earth days and a rotation period of 243 Earth days. So again, a rotational spin is complete from day to night. There are approximately 2 Venusian solar days in a Venusian year. It's pretty mind-blowing. Now let's compare Venus's atmosphere. Let's talk about it first and then compare it to Earth. So Venus has a hot, dense atmosphere and a corrosive cloud layer. So the toxic gases and the clouds will eat away at you if you were out there, or if you were in some sort of spacecraft perhaps. But I was going to say the clouds are thick. Oh, what's going on here? Okay, so we got the pressure, we have the altitude, right, from the surface going all the way up. We've got temperature in Kelvin, but you want to see temperature in Celsius. Okay, so spacecraft measures reveal 96.5% of the Venusian atmosphere is carbon dioxide. Remember, carbon dioxide is a heat-loving gas. It takes in the heat and it gives off heat. So, and most of the balance of the atmosphere is the remaining nitrogen. Venus clouds consist of droplets of concentrated sulfuric acid, and this causes a huge amount of atmospheric pressure, 90 atms, and the surface temperature is 460 degrees Celsius, again, at the surface. So if you just look over here on the graph and you go all the way down, it's really hot at the surface, over 400 degrees. Both temperature and pressure decrease as the altitude increases. You guys remember we were looking here at sea level in the troposphere. You could see that the temperature at the surface is about 15 degrees. And if you were to go up to about, let's say this is 10 kilometers, let's stick with 10 kilometers, your temperature would go down to about negative 55 degrees. So now if we kind of compare both of them, right? So if you have 10 kilometers up, okay, that's about right here, 10 kilometers up. All right, you'd still be pretty hot. So you'd still be about like 400 degrees Celsius. Now, our temperature line graph swings back and forth, but Venus just pretty much decreases all the way. So if you go up to 100 kilometers up, you'd be about negative 100 degrees. So that would be, let's see, for us, that would be right about here. And the temperature would actually be much, much warmer. Okay, somewhere between, so about 50 degrees Celsius. The upper cloud layers of the Venusian atmosphere move rapidly around the planet in a retrograde direction as well, with a period of only about 4 Earth days, meaning that it takes those clouds to revolve around the surface, to move around the atmosphere of Venus in about 4 days. Pretty crazy if you think about it, because if it rotates so slow, its clouds are really moving. In the atmosphere, we have convection currents going on, right? And if you remember this graph, There are many convection currents going on above the surface of the Earth. This is our equator right here. Okay, Earth rotating rapidly, of course, compared to Venus. And we have these different convection cells going on from the equator all the way to the North Pole. Okay, we have various ones. And there's 6 convection cells total from the northern to the southern hemisphere. The convection belts of the Venusian atmosphere is dominated by only 2 huge convection currents in the cloud layers, one in the northern hemisphere and one in the southern hemisphere. So again, you could see that the sunlight warms the equatorial regions, and there's only one northern cell and one southern cell, compared to the one, this diagram here, and matching this diagram over here from our reference table. You can see this is the equator, and we have 1, 2, 3 in the northern hemisphere, and then an additional 3 in the southern hemisphere. Okay. Volcanic eruptions are probably responsible for Venus's clouds. Venus's clouds consist of droplets of concentrated sulfuric acid, and active volcanoes on Venus may have been a continual source of this sulfurous material. So out of volcanoes comes sulfuric acid, water vapor, methane, carbon dioxide, etc. The density of craters suggests that the entire surface of Venus is no more than a few 100 million years old. According to the equilibrium resurfacing hypothesis, this happens because old craters are erased by ongoing volcanic eruptions. So remember, volcanoes, when they erupt, they produce new surfaces and new features, and then erosion will go ahead and erase it away. Here are some features. The Mat Mons volcano, a young lava flow from Mat Mons, evidence of volcanic features. Another lava flow here, which is over 500 kilometers in length. Here's another picture from the Venera 13 probe. Some rocky, it's fractured lava, maybe. But since we're talking about climate, this is our last week of climate, what's interesting is that and how the climate of Venus differs from Earth and why that is. So Venus's highest temperature is caused by the greenhouse effect. We call it a runaway greenhouse effect. And as the dense carbon dioxide atmosphere traps and retains the energy from the sunlight, it also traps it, it absorbs it and gives it back. The early atmosphere of Venus contains substantial amounts of water vapor. And this caused a runaway greenhouse effect that evaporated Venus's oceans and drove carbon dioxide out of the rocks and into the atmosphere. Almost all of the water vapor was eventually lost by action of ultraviolet radiation on the upper atmosphere. The Earth has roughly as much carbon dioxide as Venus, but it's been dissolved in Earth's oceans and chemically bound in its rocks. So the Earth does absorb Earth's oceans does absorb carbon dioxide, which then eventually gets into the rocks. So this is a recycling of carbon dioxide here on Earth. You have water vapor, CO2, sulfuric dioxide. They are recycled. So in step number 1 here, you see coming out of the crater of a volcano, not only lava, but gases such as those 3 that I just mentioned. They're outgassed from volcanoes, along with methane that we talked about last week. And then the water vapor will cool and condense, form rain clouds through the process of condensation, release rain, and cleans out the atmosphere, bringing down carbon dioxide and sulfuric dioxide into the ocean. So it gets dissolved in there and then gets absorbed into the sediments and therefore becomes sedimentary rock as well. And if it gets pushed down deep enough through the motion of plate tectonics, it gets abducted enough, it'll go down to great depths, and therefore, the deeper you go into the crust, the hotter it gets, melting the rock and then becoming magma, which then will rise back up through a magma chamber and through the neck of a volcano, releasing it back into the atmosphere. So that cycle continues. Now, on Venus, however, there is not a recycling process whatsoever because everything is just hot. So what happens is you have no recycling. You have those gases going through a volcano, there's no water anymore to dissolve those gases. Therefore, the carbon dioxide just gets put right into the atmosphere. Some of the water vapor and sulfuric dioxide, they'll combine to form sulfuric acid in those Venus clouds. Remaining water molecules, they break apart due to the ultraviolet radiation from the sun because there's no ozone to absorb the ultraviolet radiation in the Venusian atmosphere. So remaining sulfuric dioxide molecules are locked in the minerals on Venus's surface. So the surface of Venus shows no evidence of plate tectonics anymore. It seems as though it's geologically dead. The surface of Venus is surprisingly flat, mostly covered with gentle rolling hills. There are a few major highlands and several large volcanoes. So highlands causing maybe from like uplift, dome action going on, kind of like bubbling of magma underneath. Not necessarily folding or mountains being formed. But the surface of Venus shows no evidence of large crustal plate activity, which actually plays a major role in shaping the Earth's surface. Here are some of Venus's features and some of their names: Aphrodite Terra, the Atlantic planet, and I like this one, Phoebe Reggio, just to name a few. So, recapping plate tectonics for the Earth. So down here it says Earth, the crust is cool, it's rigid, stiff, and so you can move it in large plates when underneath it you have melted rock and convection currents going on in the asthenosphere. So new crust is created at mid-ocean ridges when they separate, and then you have crust being destroyed at subduction zones where you got conversion going on, right? But Venus, however, so you got something hot down here, you got something cool up here, so that allows movement. But it's hot all over on Venus. It's like the crust is too hot and too soft to move in rigid plates. The absence of water may limit motion. So just sit tight. I got to plug in the battery. I'm back. Okay. All right. So I kind of think of this as like partially melted wax, like underneath and on top. So you have compression and pile up over downwellings. You got a hot plastic crust and extensive volcanoes over upwelling. So it's just hot. If it's all the same temperature, then you don't really have true convection cells going on if everything's all the same temperature. Remember, you got convection going on when you have different temperatures and different densities. This crater was formed by a meteoroid impact, and later a fault in the crust formed this deep valley, destroying half of the crater. These streaks are other fractures or faults that have occurred since the crater was formed. The Guillemins. Pretty cool. Venetian surfaces. Ridges formed from compression at that surface, so compression going on like here, right? Evidence of that. And wow, we're done. Okay, so basically, what I wanted you to realize is that Venus's direction of rotation is different than all the other planets in the solar system. Why it is, scientists still are figuring it out. There's some information out there, but we're just touching on it lightly. There is some volcanic activity that there's evidence of volcanic activity on the surface of Venus, but it is geologically dead because it's hot underneath and hot on top, not plate movement, no more plate movements going on. And the runaway greenhouse effect, the climate of Venus is very different due to the climate of Earth because of the different composition of our atmospheres. It is just loaded with carbon dioxide, which is a big concern for Earth. That's why we're so concerned if we have too much fossil fuels being burnt, then you're being used and you're pumping more carbon dioxide into the atmosphere. And then it just, it starts to just run away from you and then causes temperatures to increase. So that's it. Next week, we will talk about weather. And I hope you enjoyed this edition of Some Good Science. We'll see you next week.